Welcome to our educational series on physics. In this video, we'll explore the fundamental concepts that form this fascinating field. Physics seeks to understand the laws governing the universe, explaining everything from the smallest particles to vast galaxies. Studying physics not only demystifies the physical world, but also sharpens your problem-solving skills. During this journey, you'll dive into Newton's laws of motion, principles of energy, and quantum mechanics. Get ready to uncover the elegance of nature's laws and gain a newfound appreciation for the physical phenomena around you. Welcome to our deep dive into the world of physics. In this segment, we'll explore physics, the science that studies matter, energy, and their interactions. Physics is divided into branches such as mechanics, thermodynamics, and electromagnetism. These branches explain the principles governing the universe and play crucial roles in our everyday lives. From smartphone technology to weather patterns, physics surrounds us. As we delve into these topics, you'll see how physics shapes our understanding of the world. Now let's begin by defining what physics truly is. The scientific method is a systematic approach to research crucial in physics. It starts with observation, forming hypotheses, and rigorously testing them through experimentation. Conclusions are then drawn, supporting or refuting the initial hypothesis. This process enables us to explore and understand the underlying principles of the universe. The scientific method has led to groundbreaking discoveries, from Newton's laws to modern quantum mechanics, ensuring findings are robust and reliable. We'll illustrate how these concepts apply to various physical phenomena, showcasing the power of the scientific method in action. Welcome back. In this segment, we dive into classical physics cornerstone, Newton's laws of motion. Isaac Newton, a towering figure in scientific history, laid down three fundamental laws describing the relationship between a body and the forces acting upon it. Let's start with the first law, the law of inertia. It states a body remains at rest or in uniform motion unless acted upon by an external force. Moving to Newton's second law, introducing the equation F equals ma. Here, F represents force applied, M stands for mass, and A denotes acceleration, quantifying the effect of forces on motion. Finally, the third law. For every action, there is an equal and opposite reaction. This explains why when you push against a wall, it pushes back with the same force. Newton's laws explain the principles governing motion, from a speeding car to the gentle fall of a leaf. Their simplicity belies profound depth, shaping our comprehension of the universe. As we proceed, you'll see how these principles apply to energy and work, expanding our grasp of physical interactions. Stay with us as we continue this exciting journey into the depths of physics. In this segment, we delve into two fundamental concepts in physics: energy and work. Energy is the capacity to do work, fueling remarkable processes around us. Various forms of energy play crucial roles in different scenarios. Kinetic energy is the energy of motion. When a cyclist pedals, they convert chemical energy from muscles into kinetic energy. Potential energy is stored energy, ready to be unleashed. Picture a roller coaster at its peak. It holds immense potential energy, waiting to convert to kinetic energy as it races down. Thermal energy, felt as heat, results from microscopic particles' movement within substances. Electrical energy powers our homes and devices, while chemical energy drives biological processes and industrial reactions. These forms of energy transform and transfer seamlessly. Let's introduce the work energy principle. Work is performed when a force acts upon an object to cause displacement. The work done on an object equals the change in its energy. Imagine pushing a sled across the snow. The energy expended varies depending on the force applied and the distance the sled travels. This principle bridges energy and work, showing how energy performs tasks. As we explore these concepts, we'll appreciate their interconnectedness and impact on the physical world. Stay tuned as we unravel more principles governing our universe. The law of conservation of energy is a fundamental principle in physics. It states that in a closed system, the total amount of energy remains constant. Energy can transform from one form to another, such as from kinetic to potential energy, but it can't be created or destroyed. Consider everyday examples. When you ride a bicycle downhill, potential energy converts into kinetic energy. When you apply brakes, kinetic energy transforms into thermal energy. This law has profound implications, requiring us to account for all energy transformations. It serves as a cornerstone in understanding energy flows within different systems. We'll see how this principle applies across various domains, shedding light on the intricate dance of energy throughout the universe. In this segment, we dive into thermodynamics, a branch of physics governing heat, energy, and work. Thermodynamics plays a pivotal role in understanding energy transfers within physical systems. The first law of thermodynamics, or energy conservation, asserts that energy cannot be created or destroyed, only transferred or converted. Essentially, the total energy in a closed system remains constant. The second law of thermodynamics introduces entropy, a measure of disorder within a system. It states that in any energy transfer, the total entropy of the system and surroundings will either increase or remain unchanged, illustrating why some processes are irreversible and natural processes tend toward increased disorder. The third law of thermodynamics defines absolute zero, the theoretical lowest temperature where a system reaches minimum entropy. Absolute zero is the point where molecular motion virtually ceases, serving as an essential reference in thermodynamics, although it is practically unattainable. Understanding these laws allows us to grasp how energy flows and dictates matter's behavior in our universe. These principles often intertwine with other areas of study, shaping our understanding of the physical world. Moving forward, we'll see how these thermodynamic principles apply in various scientific phenomena and everyday applications. Electromagnetism, a cornerstone of modern physics, delves into the intricate dance between electric and magnetic fields. These fundamental aspects of nature intertwine in ways that power our technology and shape the universe. We'll start with electric fields, force fields surrounding charged particles, exerting forces on other charges. Picture the static cling from a balloon. That's an electric field at work. Magnetic fields emanate from moving electric charges and magnetic materials like iron, creating effects seen every day, from compass needles pointing north to electric motors functioning. James Clerk Maxwell unified electricity and magnetism, revealing changing electric and magnetic fields generate each other, forming electromagnetic waves like visible light, radio waves, and X-rays. These waves travel through space, carrying energy across vast distances. Wi-Fi signals connecting devices are the work of electromagnetic waves. Understanding these fields' interactions explain phenomena, from auroras to MRI machines. Moving forward, we'll see how these principles apply in advanced technologies and everyday life. Waves and oscillations are fundamental concepts that ripple through the world of physics. Waves transfer energy from one place to another, manifesting as mechanical or electromagnetic waves. Mechanical waves, like sound waves, require a medium to travel, while electromagnetic waves, including light waves, propagate through a vacuum. Understanding wave properties is crucial. Waves have characteristics like wavelength, frequency, amplitude, and speed. Wavelength is the distance between successive crests or troughs. Frequency is the number of waves passing a point per second. Amplitude measures the wave's height from its resting position. Wave speed is how fast a wave travels. These properties determine wave behavior and applications. Waves influence nearly every aspect of our lives. Sound waves allow communication, music entertains us, and ultrasounds examine internal body structures. Electromagnetic waves enable technology like radio, television, and the internet, shaping modern society. Moreover, studying wave behavior extends to fields like seismology, helping understand and predict earthquakes. As we delve deeper, we'll see these principles' pervasive influence and utility in various science and technology domains. Understanding waves unveils physical world mysteries and equips us with tools for innovation. Stay tuned as we explore the next physics topic together. Optics, a cornerstone of physics, delves into the fascinating world of light and its interactions with matter. At its heart, optics includes reflection, refraction, and the use of lenses and mirrors. Reflection is the process by which light bounces off a surface. Imagine a light ray striking a mirror. It bounces back, following the law of reflection. This principle is essential in understanding how we see the world around us. Refraction occurs when light passes from one medium to another, changing direction. Picture a straw in water appearing broken. This is light bending due to its speed changing between air and water. Refraction is crucial for applications, from simple glasses to complex scientific instruments. Lenses and mirrors manipulate light uniquely. Lenses, convex or concave, bend light to focus or diverge, performing essential roles in cameras, telescopes, and glasses. Mirrors, flat or curved, reflect light precisely, aiding in everything from household mirrors to telescopic systems. Optics leads to innovations in photography, astronomy, and medical diagnostics. Understanding light behavior enhances our grasp of fundamental physics and propels technological progress. In the next topic, we'll explore the quantum realm, where light exhibits both particle and wave characteristics. This behavior challenges classical interpretations and introduces revolutionary concepts. Stay tuned as we unravel quantum mechanics mysteries. In physics, quantum mechanics delves into particles' behavior at atomic and subatomic levels. One fascinating concept is wave-particle duality. A particle, like an electron, sometimes behaves as a discrete particle and at other times exhibits wave properties, challenging our classical understanding. Next is the uncertainty principle, stating we cannot simultaneously know both the exact position and momentum of a particle. The more precisely we determine one, the less precisely we can know the other. This inherent uncertainty underscores quantum mechanics' probabilistic nature. Moreover, quantum states reveal peculiar quantum superposition. A particle can be in multiple states at once until it is observed, collapsing into a single state. Schrödinger's cat thought experiment illustrates this, where a cat can be both alive and dead until observed. These principles expand our understanding of the microscopic universe and pave the way for technologies like quantum computing and encryption. Moving forward, we'll illuminate how Einstein's theories of relativity changed our understanding of space, time, and gravity. Relativity, introduced by Albert Einstein, reshaped our understanding of space, time, and gravity. Let's delve into the two branches, special relativity and general relativity. First, special relativity. This theory deals with objects moving at high speeds, comparable to the speed of light. It introduces ideas like time dilation and length contraction, where time appears to slow and lengths contract at light speed. This alters our classical notions of time and space. General relativity extends these principles to include gravity. Instead of viewing gravity as a force between masses, Einstein described it as space-time curvature. Mass and energy tell space-time how to curve, and curved space-time tells objects how to move. This elegant theory provided insights into planets, stars, and the universe. Relativity revolutionized our understanding of black holes, predicting their existence long before observation. It paved the way for technologies like GPS, relying on precise time measurements adjusted for relativity effects. Predictions about the universe's expansion opened new vistas in cosmology, leading to Big Bang insights and our cosmos's fate. Moving forward, we'll see how these principles set the stage for modern physics, reshaping our perception of the universe at cosmic scales and within the smallest particles. We'll explore atoms' intricate structures and behaviors, the building blocks of matter. Atoms are the fundamental building blocks of matter. They are composed of protons, neutrons, and electrons. Protons and neutrons reside in the nucleus, while electrons orbit around it. Various models explain atomic structure, from Dalton's solid sphere model to Bohr's planetary model, each providing unique insights. Today, our understanding of atomic theory has vast applications, from medical imaging to advanced materials. Recognizing atomic structure details helps grasp matter's essence. Moving forward, we'll see how atomic theory principles extend into nuclear physics, shedding light on forces binding the atomic nucleus and powerful reactions resulting from interactions. Nuclear physics delves into the atom's heart, revealing powerful phenomena within its nucleus. It explores nuclear reactions releasing immense energy. Radioactivity involves spontaneous emission of particles and energy, transforming elements. This field encompasses practical applications, from nuclear power generation to medical treatments and scientific research. Understanding these principles gives insights into the universe's creation and cutting-edge technologies. As we move forward, you'll see how these profound concepts shape our world in unprecedented ways. Particle physics explores the universe's building blocks, fundamental particles, and their interaction forces. The standard model categorizes all known elementary particles, quarks, leptons, and gauge bosons, revealing cosmic harmony. Particle physics isn't just theoretical, it has applications in medical imaging technologies and materials science advances. Discoveries in particle physics pave the way for groundbreaking innovations. Moving forward, we'll see how these fundamental principles form our understanding's backbone, bridging the smallest particles and cosmic phenomena. Astrophysics broadens our understanding of the universe by applying physics to celestial objects and phenomena. It reveals stars' intricacies, galaxies, and the cosmos's overall structure. This field examines objects beyond our reach, from individual stars to galaxies, delving into cosmology, studying the universe's origins, evolution, and fate. Understanding these laws unlocks space and time secrets. Astrophysics advances scientific knowledge and practical applications, like navigation systems improvements. Moving forward, you'll see how physics principles illuminate our universe's mysteries. Let's address some common misconceptions in physics and clarify the correct concepts. The myths. Gravity is stronger on heavier objects, vacuum means empty space, and light travels instantaneously. In reality, gravity's acceleration is the same for all masses. Vacuum contains fields and particles, and light has a finite speed. Dispelling inaccuracies fosters a deeper understanding of universal principles. Moving forward, we'll see how these corrected concepts play crucial roles in advanced topics. Let's review key concepts discussed. We covered physics significance, fundamental topics like Newton's laws, energy principles, thermodynamics, and electromagnetism, and quantum mechanics realms. These principles provide a foundation for understanding the physical world, opening doors to further physics exploration and discovery. Grasping these concepts is essential for advanced studies. Continue your journey, dive deeper into topics, and let curiosity lead the way. Moving forward, more opportunities await to explore physics wonders. To continue your physics journey, here are recommended books and resources. Start with Physics for Scientists and Engineers by Surway and Jewett for in-depth understanding. For quantum mechanics, Introduction to Quantum Mechanics by David J. Griffiths is excellent. The Feynman Lectures on Physics offer comprehensive topic overviews. Online, check Khan Academy and MIT OpenCourseWare for free courses. Websites like Hyperphysics and Physics Classroom provide great explanations and interactive tools. Dive into resources, experiment with problems, and expand your knowledge. Remember, Knowledge Quest is never ending. Explore, question, discover. Thank you for joining us on this physics journey. Your curiosity and passion drive us to create educational content. If you enjoyed this video, subscribe to our channel to stay updated on our latest videos exploring physics' fascinating world. Don't forget to explore our other educational content. There's always more to discover. Together, we can demystify the universe's wonders, one concept at a time. Thank you for watching, and see you in the next video.